very much. Hi, everyone. I'm not sure how many of you have been on the last presentation, but basically we cover some things from before, and we are just going to remain from that point. If someone haven't been there for the last presentation, he can ask me whatever he wants and whenever he need. I will occasionally jump back to the Zoom just to see is there a raised hand. You can also ask the questions in the comment section. I will try to answer it all as much as I know. So last time we spoke about just some baby steps in soil mechanic. We just covered some what the soil mechanic means, so some history aspects of it. We spoke little bit of the Colombo and the Terzaghi as well. We spoke about like how everything started, how the modern soil mechanics started, and then we finished everything the lesson from the failures. Here we had we already spoke about that. We just covered that failure there. We just described some stuff so you can get the feeling how much the soil mechanic is actually important. And we are going to proceed with some other stuff, some baby steps into soil mechanic. Of course, to actually understand soil mechanics, you need to understand some basic stuff. First of all, those baby steps are what's actually soil, and how to actually describe soil, and how to describe what's the soil and what's actually just weak rock. So soils are formed from the physical and the chemical weathering of rocks, and the physical weathering involves reduction of the size without any change in the original composition of the parent rock. The main agents responsible for the process is exfoliation, unloading, erosion, freezing, and thawing. We also have the chemical weathering that causes both reduction in the size and the chemical alteration of the original parent rock. The main agents responsible for the chemical weathering are hydration, carbonization, oxidation, and often the physical and chemical weathering take place in concern. So what we usually have, if the soil remains on site after weathering, we call it residual soil, and those soil retain many of the elements that composite of the parent rock. So it's really important to actually have the feeling what was the bedrock if we have residual soil. Uh, Through this, we are usually not having the residual soil because every time in nature you have wind, you have water, you have chemical weathering as well. So those soils are moving during the longer geological time. Sometimes like a few hundred years, we have soils that is already moved. So that's when we need to define what kind of type of soil it is by the origins. So really important stuff as well is to define what kind of type of soils we have, because not every soil is the same, especially when it comes to geotechnical engineering, when it comes to calculation some stuff, when it comes to soil mechanic. You need to define what kind of soil you have as the first parameter you're going to need for everything after that, because we do those stuff to actually calculate something, to actually have some proper meaning in it. And if we can group the soils in some groups, and we already know what kind of the material properties we can expect from those soils, you can understand that's really important to just group the soils as they should be grouped. So we usually there's some basic terms are just gravel, sand, silts, and clay that we use to describe the texture of the soil. You know all those terms because it's something that everyone using in a just real world, especially like gravel and sand and clay. So still not that much. So that's just texture. Texture also refers the appearance of the or feel of the soils. So sands and gravels, you're going to have like a group together and as cross grain soil, and the clays or silts are fine grain soils. So basically, when you go to the deeper to the soil mechanic, what this means for you is you have two really important mechanical parameters for some soil models, and that's friction of angle and cohesion. A really important thing for you to remember is that coarse-grained soils do not have cohesion. Everything they rely on is the angle of friction, internal angle of friction, and the fine-grained soil actually have cohesion and have friction angle as well. So the coarseness of the soils is determined by the knowing of the distribution of the particle size, which is a primary means of the classification of coarse-grained soils. And to characterize fine-grained soils, we need further information of the type and the minerals of the soil that we have there. This response of the fine-grained soil to the loads, known as the mechanical behavior, depends on the types of the predominant mineral that is present in the soil. So when we speak about the origins of the soil, we have plenty of origins of the soil. What we usually have is alluvial soils. Those are usually fine sediments that we have eroded from the rock, and those are transported by the water and have settled on the riverbeds and stream beds. So basically, every city that have river have alluvial soils, and even some that don't have a river at this moment, but that they had a river like in some geological historic time, they have alluvial soils. Alluvial soils are usually related to the really flat area. So you can be sure if you're going to do some geotechnical investigation close to the river, close to the water stream, close to the any kind of water, you can say that you have alluvial soils. Usually, the composition of the alluvial soils are gravel, sands, and clay. Usually, that clay has some organic matter as well that you need to be really careful about. Second soil we have, a really common soil, is a colluvial soil. We call it colluvium. Those are soils that you can find at the base of the mountains and that have been eroded by the combination of the water and gravity. The main part here is gravity. You need to remember those soils because they are related to the landslides. Basically, a landslide, when you have landslides, you have like a soil that have been moved by gravity. And at the moment, when soil is moved by gravity, you need to call it colluvium soil. That can be different. It's usually clay because clay is easiest to move and it's the most unstable soil. So when you're going to deal with the landslides, you're going to have a lot of colluvial soils because if you don't have landslide, you don't have colluvial soils, basically. Then we have aeolian soils that are made by moving some particles of the soils by wind. For those that live more in the desert parts of the world, that is more dry part of the world, you have aeolian soils. In Europe, there's not really much of it. Some of those soils are actually more related to the volcanic ash we have, and then they just moved by the wind and then make some deposit, and only then we actually have aeolian soils. But for those people that live in a really dry area, actually you're going to deal with aeolian soils. We also have expansive soils, and those are always clays, or sometimes they're sealed. As the word itself is going to say, the expansive soils are soils that.
Yeah, Safet, I'm sorry to interrupt you. Someone is requesting in the chat that the slides, as you're going through the presentation, they are not moving.
Oh,
They're not
really?
advancing.
Okay, that's.
Thank you.
Can you? I'm just going to stop sharing. Try to share again. Is it moving now? Or just on one?
Yes, now it's moving. Yeah.
Yeah, okay, that's good. That's good. So let's go full screen. It's moving now.
No, it's not going full screen, Safet.
Oh, okay, so it's when it's on full screen, it doesn't work for some reason. Let's just keep it like this. I think I hope everyone can see it. Okay, now it's good. I hope so. So yeah, we spoke about expansive soil. So it's usually clays, and it depends of the mineral composition of the clays. Uh, the as the word said, they just expand and shrink, uh, and they can be really difficult to deal with. If you're going to have problem with the expensive soils, you're going to have some issues, uh, especially where you have like weather that's like sometimes dry, sometimes wet. That's usual weather in Europe and in some parts of the US as well. Um, when you actually know what the bedrock is, you can you can assume that you're going to have a expensive soil. It's usually when you have like a gypsum, you're going to have a expansive soil. When you have some kinds of the organic soil, you also can assume that you're going to have expansive soil as well. The thing with the expansive soil, you can test in the laboratory, and you will see. Next lecture we are going to cover the laboratory test, and we are going to speak about odometer test. We already spoke about that at the first lecture we had. So odometer test is basically you have soil sample and you just press it to some kind of load and you're measuring displacement. And if you're going to see that your displacement are actually going, usually you just add water and you'll see that actual displacement are, are going in a different way. You'll just okay, that's expensive soil. Important thing is to determine how much of the pressure that expensive soils is actually having, so you can design everything you have good enough to actually not be lifted up. So then we have glacial soils that are related to the glacier and mostly to the ice age we had 200,000 years ago. We have some of those in Europe. We have a lot of problems with those, especially when it comes to highway, because they're really heterogeneous. They're a mix of the rock debris, sand, sealed clays, and the boulders. So when you have glacial soils, it's really hard to actually define what your material parameters here are as, and it's really hard to actually model and calculate those stuff. So for those things, you need to really be careful, and it's hard to do geotechnical investigation on them because all you can drill your geotechnical borehole and you're going to have clay, and then 10 meters from that borehole, you're going to have like just plain rock, just huge block. And when you deal with the glacial soils, you're usually going to design uh, as you excavate during the project itself. So and that can that can come with some problems with actually like finance problems because you couldn't really predict uh, what you're going into. So just be careful with the glacial soils. Mud, we also have mud. It's usually related to the lakes and the coal. If you have really geologically young coal, you will have mud. Mud is the clay and silt mixed with water. The problems with mud is uh, you usually have problems with the settling of the buildings in mud. So sometimes it's hard to design. It's not hard to design. It's just expensive constructions when you have buildings on mud. And when you have mud, you cannot make slopes. So you can, but it's like too expensive. It's better to just move everything you need to move and then actually deal with that. Then if you're going to design in mud, you need to be really careful because it's acts like water, and you have mud flows as well. You probably saw that on YouTube somewhere. It's like huge amount of the water with the clay just going there and like covering everything. But those are some stuff that you need to be careful with because it's really hard to design on them. It's expensive to design on them. There's also like plenty of different kind of soil, but those are just things that we usually deal with. So you also have a calcareous soils, cliche, the glacial till, talus, glacial clays, scree, gypsum. Gypsum is actually soft rock, the loam, mosses, marsh soils, and everything else. There's like 50 types of soil. Depends on where you are, and you're usually going to deal with similar kind of soils, and you're going to learn more about just type of soils you're actually dealing with. And you're not going to worry about some others. I did had chance to work with some of those, not all. I've worked with the alluvial, colluvial, aeolian, not that much. Expansive soil as well, glacial soils, mud. I also worked with the glacial clays. The glacial clays are usually pre-consolidated clays. So we're going to speak more about that during the laboratory test course, but that can be an issue. And talus material and scree, it's really hard to build on a scree. Those are usually blocks or like 20 to 30 centimeters rock blocks, and they're really unstable. So they're just there on there, like factor of safety one, just staying there. If you're going to move any of those, the whole things just start moving. So if you're going to deal with the screen, it's better to try to find different way and just build somewhere else. You don't want to actually build anything there, especially highways. You can build there with the deep foundations, and thus it's really important to have proper geotechnical investigations. But if you have like 30 or 40 meters of scree, doesn't make sense. It's not economical to drill there. It's not economical to build something there. It's just going to be too expensive. Just try to avoid those kind of soils. So we usually just
Safet,
yep.
Safet, really sorry to interrupt you again. If you could be perhaps kind enough to increase the zoom of the slides to perhaps 75 to 80%, so the font is a tad bigger to the eye, then the chat would appreciate that.
Okay.
Thank you.
Let's see. Is this working?
Yep. Now it's bigger. Thank you very much.
Okay. Let's see. Just are the slides are moving now?
Yes, they are.
Okay, that's perfect. Yeah, sounds good. So we usually just define our soils based on the particle size. That's the first thing you're going to do. You have different kind of the soil classification system. The most common ones is just Unified Soil Classification System or UCS. That's coming from the American Society. We also have the one specific for the American Society, ISTM, and some just from highways and British standards. We also have the European specific one. We are not going to cover the European one because you're usually going to deal with the just unified soil classification system. If you're going to learn that one, you can work with any other. So those are just the difference we had between different kind of the standards. British standards covered clay and then expand sealed sand and gravel in some smaller groups. And then by the end, you have cobbles and boulders. Uh, the most important thing for you is to see those grain size there on the epsilon axis, and you will see that every of those classifications actually define what's the difference between clay and silt, what's the actual border between clay and silt when it comes to the particle size, what's the border between silt and sand, what's the border between sand and gravel, and go on. So basically, if you learn one, it's not that hard to actually just just go with another one, depending on what is a requirement for the project, what's your government official standard. So you can just learn one and just move on. We're going to speak about America, the unified one mostly. So how to actually define grain distribution in laboratory? You can define when you go on site. You will see something is clay, something is gravel, of course. Uh, but there's distribution. Distribution means how much of the soft of the fine particles you have, and how much of the coarse grain particles you have. So there's one test that's called grain distribution test. You have one for the coarse grained and the one just for the fine grained soil. So we are going to cover those things in the lectures for the laboratory testing. But this is one how it actually looks like. So you can see, hmm, where's my laser? Okay, this laser. So you go to the lab. You have 5 kilograms of your sample you got on from the excavation pit. You go there. You have different sieves, and those sieves are made by some of the standards. You use European ones, and you have 10 different sieves. The top one is with the biggest sieve, the uh, biggest cross, and then the last one is the smaller one. Usually, just weight what you have of your sample, put everything on top, and just shake it. It's usually automatical shaking for the European, and you just measure how much of the material you have on the different kind of sieves. So you're just going to enter those things in the software, or you can calculate by hand, but reality is that you're going to use software, and you're going to have this distribution curve, and that curve is going to tell you how much of the mass or the percentage of the soil actually belong to one of the group. So if you're going to look at this one, you'll see that you have some kind of the sand, but mostly most of the curvature is in the silt and a little bit in the clay. So you will call this just sandy silt or sandy silty clay. And if you're going to go at the last one, you can see you have everything there, starting from the coarse gravel to the clay. So it's a bit mixture. So you can see that the name here, clayly gravel with sand. You're not usually going to deal with those stuff because you usually have something more uniform, especially in the alluvium. So you can see here it's like mostly fine sand. It's really uniform, mostly medium sand, and the gravel sand. You can just see it here. Okay, this is sand part, this is gravel part. You give it a name. According to ISTM, that everyone who's going to work in US is probably going to work with ISTM standards. So you have gravel, you have sand, you have silt, and you have clay. And the gravel, it's just a description of the gravel, the rounded and angularly blacky hard rock. And this part here is important to you. So you can just go back and see, okay, this is gravel. Those are 2 millimeters to 64, so 63 millimeters. That's it. Sometimes for the different kind of the standards, just different borders, but they are usually really close. So you have sand, silt, and clay as well. The most difference is with clay. Here is like less than two micrometers, and for some is less than 6.4 micrometers. That's actually like most difference you have. Let's actually go into some basic of the soil mechanic. Every soil is composed of solids, liquid, and gases, and it's a three-phase soil. So the solid phase can be minerals, organic matter, or usually both, especially with the alluvium soils. The space between the solids are called voids. That's really important parameter when it comes to settling. And the water is usually liquid part, and the air is usually gas part. So we're just going to call it like water and air instead of the liquid and glass. We don't want to sound that fancy. So water you have inside of soil, you call it pore water, and it's going to have a really big influence when it comes to odometer test, and when it comes to shear test, and when it comes to triaxial test, because that pore water have also pore pressure that influence of the mechanical properties of soil. And if you're going to have, you can see here is like have really important role in the behavior of soils under the load. And if you have like every void that is just filled by water, then soil is saturated, otherwise it's unsaturated. When you're going to go deeper into soil mechanics, you will see that there is soil mechanic for the saturated soils and the soil mechanic for the unsaturated soils. When you're going to deal with laboratory tests, you're usually going to deal with the mechanic of the unsaturated soil, because in most of the tests, by default, by the norm, you're going to have drainage, so you can pour your pour water can just go out of the soil, so your mechanical parameters are going to be unsaturated. And usually when you're going to model stuff and you're going to calculate stuff, it's going to be based on unsaturated mechanics, and really not that often just saturated mechanics. So as I said, that's the diagram how it looks. You have your soil particles, your like actual solid particles. Because it's particles, you cannot compact it like to be 100%. You have voids between them. You just call it voids, and those voids can be water or air, as we said before. So we can idealize the three phases of the soil as is shown. The physical properties of soils are influenced by the relative proportion of each of those phases. The total volume of the soil is just sum of all voids. It's just really simple formula that says, okay, we have volume of the soils and includes solids, water, and air. And that's basically all. And the weight of soil is just sum of the weight of the solids and the weight of the water, because weight of the air is not going to count because it's basically zero. So in the following definitions, we have been established how to describe the proportion of each constant in the soil. Each equation can be presented with different variables. The most popular is uh, just those we gave, and you should try to memorize those relationship. When you work on those relationship, think about the bread dough, in which you have to reconstruct the amount of the ingredients. For example, the amount of the flour and water. So just you can fill your soil just like that. If you're going to add too much water to the bread, it's going to be softer and more malleable. And the same phenomenon occurs in the fine grained soils as well. So if you're going to add, you will see when you're going to speak about the Attenborough limits and the laboratory tests, uh, you'll hear one term called like liquid limit of soil. So basically, at one point when you add too much water in soil, it just acts like a liquid. So we are going to cover some important physical soil states and some simple formulas that are going to help you to understand soil mechanic. So you have water content. That's probably the one test that you're going to always do, and it's needed for every test you're going to work with. So every time you're going to do some tests, you're going to deal with the water content. It's a really simple test, and water content is actual ratio between weight of the water and weight of the solids. Uh, it is in percentage. You usually have uh, 20 to 30% of the water in a clay, and with the gravel soil, with the gravel and the sands, like much lower, it's like 1% or something like that. It's going to have a much influence of your behavior of soil, and as you can feel if you're going to have more water in soil, those soil is going to be softer, so it's going to be harder to deal with. How to actually find out what is your water content? You just grab your soil. When you go to do with the geotechnical investigations, you have your borehole. You're going to get your samples. You're going to wrap that sample in foil, just plastic foil, or it's going to be some kind of container. And the important thing is that container should remain as it was, so it shouldn't be dried out. So you go to your laboratory, you take your sample, you take one portion of the sample, put in a metal container. You're just going to weight it to see how much of your soil is going to weight, and then you're going to put it in the dryer in the oven that is on 110 degrees Celsius. It's going to be there for 24 hours. You're going to get it out. You're just going to wait again, and that difference you can see here. Just multiply with 100%, and you will actually see what is your water content. Really simple. And then we're going to cover some other stuff. We have void ratio. That's the ratio of the volume of the void space and volume of the solids. Void ratio is usually expressed as decimal quantity. Just have volume of voids, volume of solids. Really simple. Specific volume is the volume of the soil per unit of the volume of solids. But just remember this one. 1 plus E. You're going to use it in a lot of calculations. Porosity is also one of the really important one when it comes to the clayly soils. Is the ratio of the volume of the voids to the total volume. Porosity is usually expressed as the percentage. So sometimes it's hard to define what's the void ratio, what's the porosity. Remember that porosity is expressed in percentage, and the void ratio is just decimal quantity. And you can actually connect porosity and void ratio. It's just N is this one, E divided by 1 plus E, or E divided by specific volume. So now you can feel what's the actual difference there. Specific gravity is one that you're not going to use that often. You're going to use some other stuff, some unit weight, for example. Specific gravity is ratio of the weight of the soil solids to the weight of the water of equal volume. And usually specific gravity for soils 0.6 to 0.8. And if you don't have tests for those, you can just assume that's 2.7 for the specific gravity, and you're not going to make mistake. Degree of saturation is the ratio, usually percentage. It's like a volume of the water and the volume of the soil, of the solids, of the voids. Sorry. If S is equal 1 or 100%, the soil is saturated. Every void you have in your soil is just full of the water. If S is 0, the soil is dry. There is no water inside the voids, just air. You're not going to have that, believe me. This one is one of the most important that you're going to use in your calculation of those like basic parameters. It's unit weight, and that's the weight of the soil per unit volume. We can also use term bulk unit weight, and it is written by the Greek letter gamma. Simple formula, and this is what you need to remember. You're going to test it usually, and you have two different ones, so a saturated one and a dry one, and you're probably going to deal mostly with the clay, and you can usually assume that's like around 18 and around 16 for the dry soil. But what this actually means, this is kilonewtons per cubic meter. So if you have 20 kilonewtons per cubic meter, that means that your soil weighs 2.2 tons per 1 cube. Why does that matter? For designs. And you can calculate effective pressure, and you basically cannot calculate effective pressure if you don't know what is your unit weight of the soil. It's also really important in tunneling when it comes to rock. It's also same thing applied for the rocks. For just the rocks have higher gamma. For the rocks are usually 2.6. That's the reason you have higher for the gravels, because the gravels are directly you got them directly from the rocks, and for some ore can be 50. So it's really important to actually put those things in design. I will show you in one model, which I hope that you can see it. So this is just one model I'm working on. If you go to the properties, you can see here unit weight. It's just different one. If you're going to change this, the results are going to change dramatically, just because of the one reason, and that is field stress, especially in tunnels. You can see it here. Unit weight. The effective stress depends mostly on the unit weight. That's basically total weight of your soil or rock, like above you, that make pressure on the ground you're going to be in. So remember that one. Uh, so relative density is mostly related to the soil, to the gravel and the sand. That's the index that quantifies the degree of the packing between the losses and the densest possible state of the coarse-grained soil, as determined by experiments. You can see here, for that, it's really important to actually know what is your void ratio, uh, and it's usually related to porosity as well. There's one table there that just defines what is your relative density to the porosity. You'll see that's like, if I have relative density 0, I have porosity 100. My relative density is 20. I have porosity of 80. And this is the terms that you're going to use when you're going to describe what kind of the gravel or the sand you're going to have there. It's usually you also can get it from the some field test, but from the field test you're usually going to do a standard penetration test. That's usual part of the geotechnical investigations. Always you're going to have boring, you're going to have standard penetration test, and based of the number of the blows, you can there's some calculations you can calculate your relative density. It's really important when you're going to design highways, on roads in general, on the coarse grained soil, or if you're going to design some kind of buildings there or the parking lot. I'm just going to go there and check if there's any questions. There is. Mm, okay, it's mostly for the issues with the slide. So let's then proceed. Swell factor, or fish swell, is the factor of the ratio of the volume of the excavated material to the volume of the in-situ material. Sometimes called borrow pit material or bank material. This is basically just volume of the excavation part and the volume of the in-situ material. So it is important when you have landfills. If you're going to have your excavation, somewhere you need to put that material somewhere else. You're going to make your landfill. It's really important to know how bigger that material is going to become, because you need to calculate the space you need for the landfill. This is that's one of the most important properties you can have in soil. Those are Atterberg limits. The physical and mechanical behavior of the fine-grained soils in lignite 4 states is just related to the clay and the silt. So you have solid, semi-solid, plastic, and liquid, depending on the water content you have in your soil. So you need to remember those D, C, B, and A points. So at the point D, the soil is going from the solid to semi-solid. at C from semi-solid to plastic, and at B from plastic to liquid, by increasing the water content. So at point A, we had, at point B, we had the soil became so stiff that can no longer flow as liquid, so it's just solid there. The boundary water content at point B is called liquid limit, and it you can see in the books it's going to be double L, capital L. As the soil continues to dry, there is range of the water content at which the soil can be molded into any desired shape without rupture. That soil state is called plastic one, and because it exhibits the plastic behavior of the soil. If the drying is going to continue beyond the range of the water content for the plastic behavior, the soil became semi-solid, and if you're going to put a load on the semi-soiled soil, you're going to see some cracks because it's not going to behave any longer as the plastic soil. The soil cannot be molded now without visible cracks that appears, and the water content at which the soil changed for the plastic to semi-solid is known as the plastic limit. PL, the capital PL. The range of the water contents over which the soil deformed plasticity is known as the plasticity index. Plasticity index is PI, and it is liquid limit minus plastic limit. Those are parameters that are really important when it comes to classification of soil. So you need to remember those stuff if you're going to deal with the soil mechanic in the future in the geotechnical investigation, geotechnical engineering in the future. So if you're going to have continuous drying of the soil, the final state is solid state. And at this state, there's no further volume change occurs since nearly all the water of the soil has been removed. So you can see, saturation of soil is actually zero. That's almost impossible. Only at the moment you're just going to put it out from the your dryer. And the water content at which soil changes from semi-solid to solid is called shrinkage limit. It's SL. The shrinkage limit is useful for the determination of the swelling and the shrinking capacity of the soil. We already spoke about that. The liquid and the plastic limits are called the Atterberg limits, after the Swedish soil scientist Atterberg, who actually invented those stuff. So we have changed the state of the fine-grained soil by changing the water contents. Since engineers are interested in the strength and deformation of the materials, we can associate specific strength characteristic with each of the solid states. At one extreme, the liquid state, the soil has the lowest strength and the largest deformation. At the other extreme, the solid state, the soil has the largest strength and the lowest deformation. So, as you can imagine, if you're going to deal with the clay, you're just going outside and pick some clay sample. You're going to add water. You can see if you're going to put any kind of pressure, just pressure it by hand, you'll see that's going to deform really easily. And put that soil sample in the oven just to dry a little bit, put it on sun just for 1 day to see that water just evaporate. And you will see you cannot really work with that soil anymore. It's really hard, and you cannot deform it just by your bare hand, but you can break it. So those are some parameters that you need to have feel about when you're going to design some stuff. There's some we already spoke of the plasticity index. We have also liquidity index. The liquidity index is the ratio of the difference in water content between the natural one and in situ water content of the soil at its plastic limits on the plasticity index. Sounds complicated. It's not really. When you're going to work in laboratory, you're just going to pick those stuff really easily. So there's just one table that shows description of the soil strength based on the values of the liquid index. So if the liquid index is like 0, that's semi-solid state, really high strength, brittle, sudden fractures is expected. If you're going to have a really dry soil, if you're going to just play with it with your bare hands, it's just going to break. really brittle. You have plastic state. That's usually what you had in like in your elementary school with the plastiline. You can just play with that. The plastic one is like, okay, you put pressure on your clay, it's just going to remain shape after you put out the pressure. So you for that you can see, oh, that's a plastic behavior. So it's not elastic, it's not coming back. You put pressure, stays the same. It's plastic behavior. Liquid state is just like water, just like mud. If you're going to have too much water inside of your soil sample, it's just going to flow like mud. You can say that you're overcome the liquid state. So those are some typical algebraic limits. The algebraic limits depends on the type of the predominant mineral of soil. If the monomorite is the predominant material, the liquid limit can exceed 100%. You're not going to deal with those stuff at this moment because we are going deeper in some petrology stuff. If you're going to deal with those kind of soil, those usually swelling soil, you're going to learn some more stuff after. I think at this level it's not that important to have whole knowledge about swelling soil and why some mineral in the soil determine how soil is going to behave, because at the start of your careers you're going just to deal with parameters and the laboratory testing model by those, and at some point when you're going to have some higher projects you're going to deal with those stuff, but those are more research stuff. For you it's important to actually know what you can expect from the soil. If you're going to have liquid limit like over 200, that's not possible. If you're going to have a plastic limit below 25, that's not possible. So that's the stuff you need to remember from these lectures. Just after when you start working, okay, and when you're going to get laboratory results, you say, oh, this is possible, and what did wrong to get those results. Just it's more about thinking, not to actually go with those. We also have the activity of the soil. That's one that came from the Scampton. You're going to hear that name a lot when it comes to correlation of the soil parameters, especially related to the algebraic limits. Scampton showed that the soils with a particular mineralogy and the plasticity index is linear. There's uh, he showed there is dependence between plasticity index and the clay friction, and those with more minerals that are swelling minerals, you have more active soils, and that's basically it. You don't want to deal with those stuff at this 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 basic level. So this is what you want to learn, what you want to have. It's sheet that is going to have everything for the classification of fine grained soil and fine grained friction of the coarse grained soil. So there's one line called A line, and those C there means that's clay, and M is silt one. So when you're going to deal with the plasticity index, okay, you have plasticity over 30 and your liquid limit is 50. You're here and your soil is CH or OH. H means that's high plasticity. So this high plasticity clay, high plasticity organic material, high plasticity silt, high plasticity organic material, medium plasticity, no, low plasticity, that's all. What is important for you is that when you have high plasticity clay, then you're going to have, usually going to have swelling clays. So when you, every of those stuff like size distribution, plasticity of the clay, atomic limits are just important for the soil classification. And this is going to be boring and it looks complicated, but during the work you'll get a bit more feeling about this stuff. I'm not going to talk, I'm not going to describe every of those at this moment because you can see that's some stuff. You're going to have presentation and just go over it. I'm just going to describe some baby stuff. As we already spoke, we have gravel, sand, and organic soils. Oh God. So just go there. Okay, I have gravel. So there's how much of the fines I have in my gravel. Okay, I have between 15 and 20% of the fines. Okay, let's go there. CU is a coefficient of uniformity that you're going to get from the laboratory and from particle distribution test. And the CC is a curvature coefficient that you're also going to get from the laboratory, from the size distribution test. Okay, we are here, and then you just go from there, and then, okay, poorly graded gravel with silt. So you're just going to have those sheets, start from things you know. We have sand, we have less than 2% of the fines. You got those from the laboratory. Okay, well graded or the poorly graded, you also can see that from the size particle distribution chart, and you're just going to see, okay, and then you're just going to see, okay, that's what I have, and that's what you're going to write in your report. Uh, so just go over it. There's no point of the going over all those stuff for the lecture because you're just going to have it as you work and you're just going to follow it as you work. You have organic soil and everything. This one I want you to have for yourself for your future, because this is whole point of having classification of the soil, is to know what kind of the properties you can actually expect. So this is just table that for the, like, any kind of soil, define what kind of permeability you can expect, what kind of shearing strength you can expect. It's really important. It's usually going to model with those parameters, what kind of possibility you have, and what kind of workability as the construction material you have. This one is important when you're going to build a landfills, and you're going to deal with the air dams. Compressibility is important when you're going to build on a soft material. Shear one is important for every kind of material, and permeability is important when you're going to deal with the soil drainage, because you want to have your soil drained, and that's all. Um, just go over it, keep it for yourself. You're going to need it for your early career for sure. What you're going to do next is actually to do some more interesting stuff, because all those classifications just sound boring and you're going to learn it on your way. So we are going to cover the laboratory test for the physical properties of the soil step by step. So we are going to speak how to actually determine the water content ratio. I'm going to show you some photos. One-dimensional flow in the water through soils, to see how to actually water go through soils, how to actually drain some water, stress strain and the elastic deformation of soil. That's most important stuff you're going to need for design. Stress pad, it's going to be super important for design as well. Consolidation of the soil is something you need to know when it comes to calculation of the settling the material, or you're going to have some settlements, especially for the building and the dams and the embankments as well. Shear strength is one parameter that you're going to need and use in any kind of the modeling. Design of the foundations, so retaining structure and the ground support. We're not going to go too deep in those stuff. You're just going to show some designs, and we're going to cover modelings of the tunnels in the rock science in phase two. We can also do some designs in phase two as well. The phase two is like a rock science program for the modeling, finite element modeling. We also can cover design of the retaining structure as well in phase two, as you wish. No, I'm not going to stuff. So I will see, is there any question we have, because we are by the end of our class. If someone have any question, now you can just ask me. Just turn on your mic and ask me if there's something that you want to know, and if there's something that you want to learn more about in the future presentations. Okay, Abdul.
Yes, go ahead, Abdul.
Thank you very much for the wonderful presentation. I really enjoyed the class. So there are a couple of things. One, I want you to actually explain to us the difference between compaction and consolidation. That's one, compaction and consolidation. Two, you are talking about when it came to the limits, we are talking about plastic limit, the Atterberg limit, but I think maybe I didn't get it very clearly on the Atterberg limit, because what I understood was the mineral limits of the soil. I don't know I don't know whether it is sufficient, or maybe you need to further explain. Number three, like you said, I don't know, maybe it's not for this class, for another class maybe, or if you can answer it, no problem. When you are constructing structures, like you mentioned, like dams, or even dwelling homes, the foundation has to be very strong to contain the weight that will be placed on it. So how do we determine the foundation, strength of the foundation relative to the structure that will be placed on it? Thank you very much.
Okay, thank you very much for your questions. When it comes to consolidation and the compaction of the soil, it is related. Consolidation of the soil you're going to determine by the it's related mostly related to the fine-grained soil, and we're going to do it in a laboratory for the consolidation test. You're going to do it on the clays, on the silts as well. Really rarely on the sands, and never on the gravel. When it comes to more the coarse grained soils, then you're going to deal with the compaction. Because the coarse grain and the fine grained soils actually behave differently. Because it's mostly related to the drainage of the soil itself. So in the coarse grained soils, you have fast drainage, and you don't need to worry about drainage at all. And in fine grained soils, you have really slow drainage, and it's really sometimes in the clay it's really hard to drain those soils. It's two different problems. It's easier to deal with the coarse grained soils when it comes to foundations. Sometimes it's harder when it comes to the slope design. When you have when you're going to have your geotechnical investigation on site, you're going to have your borings on site, you're going to have some penetration test. You're going to see how much of your soils is compacted, and if it's not enough, there is some kind of the treatment of the soils you can work on. It's usually just compaction by the physical compaction. You go there and just go like 1,000 times with the excavator. That's going to be during the construction just going to happen naturally. What you want there is to have a constant Q and QC for the compaction of the soil, of coarse grained soil. You have something that's called the modulus of the elasticity. There's one dynamical, one statical one. You're usually going to do dynamical one. There's one really simple test, and there is designing criteria how much of the elasticity modulus you want to have in a coarse grained soil. Usually, for most of the embankments and everything, it's 30 to 40 megapascals. And if it's not enough, and if you're going to test on site during the construction, and if it's not enough, you're just going to go over with the excavator or anything physical, and then if you can see that you're not doing enough, and then you're going to have some different kind of the measurements, and then you're going to have like dynamical compaction of the soil. And just go there on YouTube and type down like dynamical compaction of soil, and you will see huge cranes that dropping the huge metal objects on the soil just to have some design compaction. For that, it's really important to have QC on site, and just do like regular dynamic and static deformation testing, so you can know, okay, this is not 30 megapascals, it's less, I need to do something more. And when you go to the point it's enough, just stops. When it comes to compaction of material as well, there's some more tests that you have in the laboratory. It's like usually CBR and the Proctor test, it's called like that. That's going to define what's the best way to actually compact your soils. There's one thing called like what is the optimum moisture content of soil to have maximum compaction. And it's usually like, okay, you get like 7% of the water content you need to have in your soil to get your biggest compaction you can get. You just go there, spray your soil around with water. You will know, you will calculate how much water you need, and then do compaction to actually maximize your effort. And when it comes to consolidation, it's related to the fine grained soil. Consolidation is just answer of the soil to some kind of the load you have. It is happening on terms of the, if you have soil, we spoke about porosity, and in a clay porosity is usually 40%, and for soil that is 40% full of water, it's saturated like 100%. S is equal 1, as we spoke about earlier. When you have load, the load is going to push water from that soil, and then you're going to have your consolidation. So it's really important to have a consolidation test when you're doing with especially with soft soil, when you're actually expecting like really big settling there. So it's different. So you need to define first what kind of soil you're dealing with, and then you're going to define by the laboratory test you're going to deal with. You're going to define what criteria you're going to need for design. For all other stuff, when it comes to strength of the foundation, when it comes to Atterberg limits, for the Atterberg limits, we are going to cover that. Next lecture, we are going to speak more about laboratory tests. We are going to speak about the Atterberg limits. I did a lot of Atterberg limits, most boring tests you're going to deal with, because it's super cheap to do. When you work in the laboratory, they're not going to pay you that much money to do Atterberg limits, and it's like 2 hours our job. You're probably going to hate it. But it's really important, really good test. So we are going to speak more in next lecture about Atterberg limit test, and like in 5 or 10 lectures, we are going to speak more about actual foundation, because we need to cover how to get your parameters from the laboratory, how to define what parameters are good one, what is stress, what's consolidation, what is load, how is soil is deforming under the load, how to drain soil, how to deal with undrained soil, how to deal with the saturated and unsaturated soil, how to get all those parameters in model. And then after we go through all the stuff, then we can speak about about actual design of the foundations. So we need to go through whole soil mechanics, so you can understand how the soil is behaving, so you can understand how to design foundations, because there's a lot of soil models, and every soil model you need to define mechanical parameter of the soil. So you need to understand like every parameters before you're going to deal with the foundations. there's no point of design of the foundations if you are not going to understand what's cohesion, what's the angle of the friction, how to get cohesion, how do we know if the cohesions we got is wrong, what is saturated cohesion, what's unsaturated cohesion, and etc. So we are going to deal with those stuff like a lot later when it comes to foundation, but when it comes to atomic limits and some other stuff, it's going to be next lecture. So I hope that I answered your question, and let's move forward.
Safet, we're 8 minutes past the hour, so maybe we have time for one more question.
Okay.
So I'm gonna go ahead with Dr. Jane. Please go ahead.
Good evening, all. Hello?
Yes, we can
Yeah,
hear you. Go ahead.
Quite a simple and nice presentation about soil mechanics in agriculture. Yes. Having known that we have many types of soil, the loamy, the humus, the clay, my question is, which of the soil types is most suitable for farming, agriculture, and construction and bridges? Or is both the soil good suitable for the two mentioned? Thank you.
Thank you for your question. So we are mostly dealing with the soil mechanics in geotechnical engineering, but when it comes to agriculture, as far as I know, I'm not an agriculture engineer or something like that. I'm geotech. When it comes to agriculture, what I know is that it's best that you have organic soil. Organic soils are usually related to some kind of the organic deposit. So here in Europe, we have a lot of the deposit related young, and there's one type of coal that's not good enough for the to actually burn, to use it like energy, but it's extremely good for the agriculture. So if you're going to try to find soil for the agriculture, go with organic soil and go with the soil that you can find when you have bedrocks of the really high mineral composition bedrocks. The depending what you actually want, what you actually want to grow, you know what kind of minerals you want to have from soil. Go find out what kind of bedrock you have there, and then if that bedrock contains the minerals you want for grow anything you want, go for that soil there. There's one really good soil, basically like really soft rock. It's called pyrophyllite. And what we saw from the history, the pyrophyllite one, when you have pyrophyllite and the soil above the pyrophyllite is like extremely good for the agriculture. I think that will be it for the agriculture question. And when it comes to the building of the bridges and the like really huge structures, you don't want to do your foundation soils. Sometimes, usually when you go with the foundations in for like really big bridge, really like dams or the like really high embankments, you want to have your foundations in the bedrock because it's hard for soil to actually carry on like that big load. So that's the reason you have your laboratory test. You're going to speak about pillars of the bridges that need foundations, and if you have soil is usually like depending on where you are, there's like soil and then you have bedrock. It's really important to determine where your bedrock is. So you can lay your foundation in the bedrock because it's safer and it can carry more of the material. But problem starts when you have like really soil, or that's usually in alluvium soil next to the rivers. When you have like the 30 or 40 meters of the soil deposit, just like sand, gravels, then you're going to design like deep foundations. It's usually worked on the piles, and those piles works on the friction of the skin. You have like a 30 or 40 meters length long piles, like 1 meter wide, so it can ensure you enough skin friction of the piles that can carry like bridge foundations. So it depends how thick of the soil you have. You usually go through soil to bedrock to lay your foundations there. If it's impossible, then you need to deal with soil. It's usually really long piles, or really for the buildings are really big foundation mats, or combination mat and the piles. That's usually when you have like really high skyscrapers. So that will be all for today. I hope that I'm going to see you next lecture as well. We are going to speak about more about the laboratory test of the soils, so you can define some parameters. Then you're going to describe what's the stress and what's the deformation and everything after on, and then you're going to get into designs. So I hope you enjoyed, and see you next time.
Well, thank you, Safet. Thank you for today's presentation, and of course, thanks everyone who attended to this lecture. And we really hope to see you on the next installment of it. Thank you, and may you all have a great rest.